Okay, folks, we are on hopefully the last review session. We're going to do periodic table and bonding. Woohoo! I can't wait. All right, but we are going to start with electrons because electrons are important. It's electrons that are transferred and shared when it comes to chemical bonds. So let's just start talking about electrons and electron configuration and the information you can find on the periodic table. If you look, the electron configuration on the periodic table represents the ground state. For example, for fluorine, you read it right off of the bottom of the periodic table, and you would see that fluorine has an electron configuration of 2,7. When you and I get excited, we jump. Well, the same thing is true of electrons. They jump. They don't mutate, they don't divide in half, they don't multiply, all they do is jump. So in the excited state, what we do is we jump an electron to the excited state. You can check yourself when we talk about excited state because look, you have 9 electrons. 2 plus 7 is 9 in the original atom of fluorine, and in the excited state, there are still 6, 7, 8, 9 electrons. Okay? Now, it's important to understand that that is different from forming an ion. If you were forming an ion of fluorine, when it forms an ion, the 2,7, the electron configuration, changes to 2,8. The fluorine atom gains an electron. When it gains an electron, it becomes an ion. That has a negative charge. So charged is different than excited state. Okay, why is it important to know about excited state? 2 big reasons. Well, first of all, you need to know that as electrons move to higher energy levels, as they move away from the nucleus, as they jump, they absorb energy. That means that the further away you get from the nucleus, the higher the energy level, the more potential energy the electrons have. See, their potential energy increases. The other thing that you need to know is the bright line spectra is produced when electrons jump to a higher energy level. They jump up and they absorb energy, and then it's unstable at the higher energy level, so they fall back down. When they fall back down or drop down to a lower energy level from an excited state, they emit or release. Those words mean the same thing, energy in the form of light. We can see it. That is the spectral lines that you observe. There's one thing that's not on this PowerPoint that I want to make clear to you. If you have a mixture that shows different spectral lines, so this is your mixture, and it asks you what elements, element A or element B, are in your mixture. Let's draw element A and element B. Okay, this is element A, and this is element B. And it asks you, is element A or element B in the mixture? Now, you have to look at element A, and you see this line, and this line are all in the mixture. All 3 of element A's spectral lines are in the mixture, so element A is definitely in the mixture. If you look at B, yes, one of the spectral lines is in the mixture, but the second one is not. So element B is not in the mixture. Very important. Moving along. Okay, so periodic table, you need to know how it's organized. First of all, it is organized in order of increasing atomic number. Remember, these numbers down here, these are the atomic numbers. You can also tell right here that the atomic number is given in the key. If you need to know isotopic notation, you can look at this key and you'll see mass is written on the top left and the atomic number on the bottom left of the symbol of the element, and that's how isotopic notation is written. Anyway, the periodic table is arranged in order of increasing atomic number. Number of protons is the same as the atomic number, and it increases as you, that's the way the periodic table is arranged. You can also see that the periodic table is arranged in terms of periods and groups. You should know that groups go down and periods go across. Say it again. Groups go down, periods go across. Groups go down, periods go across. Very important not to get those two confused. Remember, we already talked about earlier in this review that the groups all have the same number of valence electrons. You can look like 2, 1, 2, 8, 1. So all the group 1 elements have one valence electron, which means they all have similar chemical properties. You can think about another word for group as family. If you're in the same group or family, you have the same number of valence electrons, which gives you similar chemical and physical properties. Similar properties because similar valence electrons, number of valence electrons. Now, the other pieces that you need to know, the broad picture, the metals are on the left side of the table, the nonmetals are on the right side of the table. See them over here? You also need to know that this step is the metalloids. You can remember the rhyme B, S-I-G-E-A-S, S-B-T-E. Again, B, S-I-G-E-A-S, S-B-T-E, those are the metalloids. You probably will need to be able to identify a metal, a nonmetal, and a metalloid. You should also understand that metallic character has to do with the placement of the metals and nonmetals on the periodic table. So as you go across, the metals are, it's more metallic. The elements on the left side of the periodic table are more metallic. As you go across, they become less metallic. And then if you look at group 14, you should realize that the metals are down at the bottom of the group in periods 5 and 6. So as you go down a group, the metallic properties increase. Again, metallic properties decrease as you go across a period and increase as you go down a group. I'm going to skip this slide and come back to it in a few minutes. Okay? The vocabulary is important. You must understand what the question is asking. For example, when they ask you about ionization energy, you need to realize that ionization energy is an energy. Look at B. It's the energy required to remove an electron. Energy. Ionization energy is an energy. Electronegativity is the one that everybody gets confused with ionization energy. Electronegativity is about attraction. It's how much one element attracts another's negative particles or electrons. It's a measure of attraction for electrons. That's C. Atomic radius is half the distance between the nuclei of two identically bonded atoms. You can picture it like this, but what's really important is that you understand that atomic radius is really the size of an atom. Okay, it's how big an atom is. An ionic radius is the size of an ion. Okay, for example, if we have an atom, that would be, let's say, magnesium. Magnesium's radius takes up 3 energy levels, 2, 8, 2. When magnesium forms an ion, it loses electrons. It's going to lose these 2 electrons, so it becomes 2, 8. The ionic radius of the cation, the positively charged ion, is smaller than the ionic radius of the atom. The opposite would be true if it was a nonmetal. Take chlorine. Chlorine's electron configuration of the atom is 287. It wants to gain an electron is 288. When it gains an electron, because it wants to have a full valence shell, there are now more electrons in that valence shell. The electrons repel each other, and because they repel each other, you get a bigger ion. So the ion, in this case, is bigger than the atom. So you can see the difference between atomic radius and ionic radius. Finally, metallic character is the ability to behave like a metal. What do metals want to do? Well, if we look at magnesium, metals have a small number of valence electrons. They want to lose electrons. So metals are, metallic character represents the tendency to lose electrons. Okay, now that we know the vocabulary, we can start to talk about the trends. Okay, really what you need to know, groups go down and periods go across. Make sure you have that vocabulary right. Then let's draw for you the electron configurations of the group 1 elements. Lithium is 2,1, sodium is 2,8,1, potassium is 2,8,8,1. So as you go down a group, what happens? So down a group, what happens to atomic radius? It gets larger. Why does it get larger? Because you have more energy levels or more shells. Do you see that lithium has 1 energy level, lithium has 2 energy levels. Here's 2. Sodium has 3, and potassium has 4. What does that mean for ionization energy, or the amount of energy necessary to remove an electron? Well, the bigger the radius, the easier it is for an electron to get lost. So because there's less attraction between the nucleus and that electron. So as you go down a group, ionization energy decreases. It takes less energy to remove an electron. How about electronegativity? If you want to reach out and grab somebody else's electrons, is it easier or harder? Well, the bigger atoms, there are all these shields in the way that are getting in the way of attracting somebody else's electrons. So because there's all this shielding, the electronegativity values also decrease as you go down a group. Now, as you go across a period, what are the trends? Well, let's see. This is lithium. The next element is beryllium, which is 2,2. The next element is boron, which is 2,3. Carbon, which is 2,4. Nitrogen, which is 2,5. Oxygen, 2,6. And fluorine, 2,7. And then neon, 2,8. So as you go across a period, what do you notice? Well, look at the number of energy levels. The number of energy levels stays the same. So what happens to the radius as you go across? What does change is the number of protons in the nucleus. For example, lithium has 3 protons, beryllium has 4, boron has 5, carbon has 6, nitrogen 7, oxygen 8, fluorine 9, and neon 10. So as you go across, it's like doing core exercises that are going to add muscle. You're adding muscle in the core, in the nucleus. As you add muscle, the attraction for the valence electrons increases. As the attraction increases, the radius gets smaller. Why does the radius get smaller? Because there's greater attraction. The electrons are literally sucked in closer to the nucleus. So across a period, the atomic radius decreases. Think about at the beach. The more muscles people have, the thinner they are, the more they suck in their gut. Now, as you get smaller, as you go across, that means they're holding on tighter to their electrons. So what does that mean for the ionization energy? It's going to take more energy in order to remove an electron from fluorine than it is going to take to remove an electron from lithium. Also, who's going to be able to attract somebody else's electrons more easily? Well, of course, the smaller atoms can reach out and grab somebody else's electrons more easily than the larger atoms. Now, if you think in terms of fluorine, a lot of this becomes easier. You can think that fluorine is the most electronegative. Look up at the slide. Fluorine's the most electronegative, and it also has, well, it doesn't have the highest ionization energy, but it has a high ionization energy. So you can use your trends, you can learn your trends based on fluorine, because as you go across, the ionization energy is increasing to get to fluorine, and then as you go down, the ionization energy and electronegativity are decreasing. Let's say that one more time. As you go across, ionization energy and electronegativity increases. As you go down, it decreases. Now say that all went over your head. Oh no, don't panic, because all this information is easily looked up on table S. So you can easily compare different elements on table S. Now, just go back 1 second, go to properties of metals. You should notice a couple things about properties of metals. First of all, we realize that metals have low ionization energies because it doesn't take much energy to remove an electron from them. Why? Because they generally have larger radii, and also because they have fewer valence electrons. So it doesn't take much energy to remove an electron from them. Now, also, we know that metals tend to lose electrons when they form an ion. Think about sodium. Sodium is 281. It has one valence electron. It's going to lose that valence electron. When it loses that valence electron, it has 11 protons and only 10 electrons. That means it's a positively charged ion. The other thing that's important to know about metals is they are good conductors of heat and electricity. Why? The reason is because they have a sea of mobile valence electrons. What does that mean? That means that whenever you have mobile particles, moving charged particles, they have to be charged. Whenever you have moving charged particles, and solid metals have moving charged particles, you can conduct an electric current. Okay, nonmetals are the opposite. Nonmetals do not have moving charged particles, don't conduct heat and electricity. Nonmetals, like chlorine, they have 7 valence electrons, want to gain 1. When they gain 1, they become negative ions. You gain a negative, you become more negative. Okay? And then you can review the other parts of nonmetals on your own. Don't forget to check table S for the trends when you're talking periodicity trends. Okay, last topic, bonding. Ionic versus molecular substances. Molecular is like MoCo, doesn't stand for Model Congress. It stands for molecular covalent. These are covalent compounds, okay, or covalently bonded compounds. What's the difference? Ionic is between a metal and a nonmetal. Ionic also means that there is an electrostatic attraction between a positive and a negatively charged ion. So it could also mean that if you don't have a metal and a nonmetal, you could have a polyatomic ion involved. Finally, ionic compounds, in terms of electrons, means that you transfer electrons. That's how an ionic compound forms. There's a transfer of an electron. That's different from covalent compounds. Covalent compounds, co means cooperate. That means they share, because sharing is caring. So they share electrons. And who shares electrons? Only nonmetals. So only nonmetals. Okay, now how does this connect to naming compounds and writing formulas? Well, first of all, you need to know this law, the law of definite proportions. The law of definite proportions states that every compound always contains elements combined in the same proportions by weight. That means that if wherever you get water from, whether it's Africa or New York or Tennessee, water is always going to be combined 2 parts oxygen, 2 parts hydrogen, 1 part oxygen. 2 parts hydrogen, 1 part oxygen, no matter where it comes from. So there's a specific way to write every formula. You can't just make up how the formulas are written. They are written with a very specific idea in mind. We're going to take a break. We'll do the last segment, and then the last segment will finish up this review.